Alright, so here we are with the 3-4 assignment. A lot of logarithm kind of rearranging. So, in these first few problems, we're going to assume that x and y are positive. The only reason they mention that is because there's a y here in a denominator, and you can't divide by 0, so whatever. Okay. We're going to use properties of logarithms to write the expression as a sum or difference of logarithms. So remember that a sum is going to come from multiplication, and a difference is going to come from division. So, we're going to go ahead and, again, expand this. So, taking a look at the first one, we've got natural log of 9 times y. So there's multiplication, which means we can change it into two different addition of logarithms. So a natural log of 9 and a natural log of y. And that's all they're looking for. Just can you expand it into two different logs. The next one is a log base 10, and you can see division, and so that means we're going to be subtracting. So we'll have log of the numerator minus log of the denominator. The next one gets a little bit trickier just because it's got a power, but remember that logs don't actually have powers, so that power is actually a coefficient out front being multiplied. So it's actually negative 2 times log base 2 of x. And so this is the second piece here where it says or multiples of logarithms. So this is actually the end result, just knowing that negative 2 can come out front. Alright, then the next one here, we can write it in a few different ways. I don't need to get too extreme, but since it is multiplying, it's log of x plus log of y. But, of course, if you wanted to get super fancy, you could have written it as log of x. I wrote that differently. Log of y cubed, but we just got done in the previous problem saying that that 3 there is actually up front, so we actually have log of x plus 3 log of y. And because of that, again, that's where I would stop, but because of that, you can actually have plus log of y plus log of y plus another log of y, because of course there are 3 of them. So, either way, again, that's a little extreme, but hey. The next one has a 1,000 that's being multiplied by x to the 4th. And so we can have log of 1,000 plus log of x to the 4th. But again, we don't usually keep the powers in a log. So we're going to take that 4 and bring it out front and end up with log of 10,000, or sorry, 1,000 plus 4 log of x. And then our last one has some subtraction because of the division, so we'll end up with natural log of the 3rd root of x minus the natural log of the 3rd root of y. Hopefully remember that roots are actually powers, and so we bring that root into the denominator of the power. So this is actually x to the 1/3 and y to the 1/3. And then the natural logs of those. And then, of course, since the 1/3 is a power, it can come out front. So we'll have 1/3 natural log of x minus 1/3 natural log of y. So just a little bit of a practice on rearranging those. Alright, so in the next one here, we're going to assume x, y, and z are positive, again, because of the whole can't take a square root of a negative and denominators and such. So, either way, we will use properties of logs to write the expression as a single. So now instead of going out into an expansion of logs, we're trying to go from the expansion back into just a single. So taking a look at this plus here, that's going to mean that we multiply. So we're multiplying x and 5, and then taking that 1 log of each of those pieces. Of course, that's a weird way of writing that, so usually we put the number first and then the letter. So, log of 5x. The next one has division because of the multiplication, so we're going to have x divided by y, and then, of course, the natural log of that. but we usually don't write it with that kind of division sign, so we'll do natural log of x over y. The next one here, again trying to write it as a single logarithm, means that this 1/5 is actually part of the exponent. So we've got log of z to the 1/5. Especially because of the shorthand here without the parentheses, it's kind of hard to see where that exponent would go, but it does go inside with the variable itself. Alright, then the next piece is that there are 4 log y's, but anytime there's a number out front, you're going to want to take it up first before you try to combine things. So y to the 4th. Alright, and so then from there we see that it's subtraction, so we're actually going to take y to the 4th and we're going to divide it by z, and then have a log base 10 of that. And so it's log base 10 of the fraction y to the 4th over z. And then our last one, where we are writing a singular log. Okay, so this 3 here is going to apply to both of these pieces. And then this 2 applies to both of these pieces, so that's kind of a lot. So our first one is going to be natural log of x to the 9th, because 3 sets of 3, it's going to be 9. And then 3 sets of 1 is just 3. And then we're going to add to that a natural log of y squared, and then also z to the 4th this time, because 2 sets of 2 is going to be 4. Then we see that addition is happening, so we're actually going to be multiplying x to the 9th, y to the 3rd, and y squared, and z to the 4th. And we'll have a natural log of all of that. Combining like terms, looks like we can make y to the 5th out of that middle piece, but otherwise it's just natural log x to the 9th, y to the 5th now, and z to the 4th as the total. Alright, then moving on to change of base. So again, this is something that your calculator already evaluates, so really you would just need to go to your math key. And then from your math key, you're going to need to arrow down to your base. I think it's option A or whatever. You'll have to go through a couple screens to get there. It'll say log base. But for those of us that don't have a TI-84, which is not many of you, instead of going there, you'd actually need to know, and this is a good thing to know, that you can change the base of any of these to one that's on your calculator, like a natural log or a log base 10. So for instance, when I learned this, I had to change every single one of these into a fraction of log of that answer in whatever base I wanted, and then log of that same base of the 2 there, or the power, I guess, of the log. So log of 7 over log of 2, and again, I still have a TI-83, so that's what I'm going to be typing in. Log of 7, log of 2, gets you your decimal of 0.9506. Doesn't say how many decimal places, so we'll do 4. So every one of these, you can just type into your calculator and get the decimal. That's all they're asking. But again, it's because you can change the base. So I'm just practicing. So again, all of them are going to be log base 10 potentially, or log natural log, just because that's the only ones that were ever given on a calculator. 8295 if you round. So it's good to be able to practice changing a base, because sometimes you're going to need to do that depending on how much you want to simplify. So 2.4837. Next one is going to be log of 259 over log of 12. So that one simplifies to 2.2362. Next one can be log of 12 over log of 0.5, which ends up being negative 3.584, oops, 49 becomes 50. And then just to switch it up, because again, we're just trying to change the base, so it doesn't matter what it is, I could do natural log of 29 over natural log of 0.2, and either way, because it's that same log idea, it's going to get us the same fraction, so, or decimal. And so if you evaluated that, or if you changed your base, either way, you're going to get negative 2.0922. It almost looks like I made an arrow instead of a 9. Okay. Still kind of looks like an arrow. Okay, moving on. Alright, so the next one here, we just want you to write the expression using natural logs, and so this is where you do need to actually know the change of base. So the change of base idea, again, is that it's the log of the larger number on top, so log, not large, but larger font. Oh, and they said natural log. Sorry, so natural log of x over natural log of 3, and we're not solving because not everything is a number, so that's the answer. The next one wants you to have a log of, again, the larger font piece over log of the smaller font piece. Oh, but they wanted natural log, hey. So again, if you used log base 8 or log base 10 or natural log, either way, as long as you did the appropriate formula conversion, it's the same. The next one here has addition happening. So log of a plus b over log of 2. Some of you might try to think that you can then change this to multiplication because of the previous ideas, but that's if it's multiplication inside, it becomes addition outside, not if it's addition outside. So this is the end result of that one. And then the last one is going to be log of c minus d, whatever that happens to be, over, right, they wanted natural logs, sorry. So natural log of that one, and then, oops, natural log of this one too. And again, it's because it's that easy that you can actually just erase whichever log you wanted for what you already did. Alright, so common logarithms are either natural log, whoa, I don't know what I was writing there, or log base 10. And again, they're called common logarithms because, well, most everything is in a base 10, but then EU is also developed because of its link to exponential growth. So those are common logs, log base E technically, natural log, and then log base 10. So this one just wants you to write the expression using only common logs. So we are going to rewrite this first one, for instance, as referencing our last problems, natural log of x over natural log of 2, but you could also use log base 10. The next one I'll just switch to log base 10, sure. Remember the larger font goes on top and then the small font or the base goes on bottom. This next one I'll go ahead and use natural log. And then maybe switch back and just do log of x minus y over log of 1/3. So again, just reiterating that idea that that larger font piece is the numerator and the smaller font or the base is the denominator. Alright, now we're going to reference back to graphing a function and analyzing it. So we're going to identify range and domain and things like that. So we're going to do log of x squared. So typing that into your y equals, we've got log of x squared. Make sure that that squared is inside the parentheses, as you can see in the typing that's happened. Alright, so if we graph that kind of on a 10 by 10 grid, so this one is unique, but hey, what's new? So the idea is it's going to kind of asymptote off here at 1, 2, 3, 4 maybe. But it doesn't, it just looks like an asymptote, but it's not, because log just grows very slowly, based on it's the inverse of exponents, which grow very quickly. So, as you graph it, it kind of looks like it teeters off over here, but it actually continues up. And then here, it actually has an asymptote at 0. And then, I guess it goes through 0, 1, or 1, 0, and negative 1, 0. So it's this kind of mirror with an asymptote in the middle. So, as we look at our domain, that's actually all real numbers, but, oops, x can't be 0. Your range, if we think about how far up and down it's going to go, again, as long as it grows slowly, even though it feels like it has an asymptote, we are going to actually say that it's all real numbers. It goes all the way down, but then it also goes all the way up when it comes to the y values. Then we have continuity. And it is not continuous. It has asymptotal discontinuity. And then we've got increasing, and then also decreasing. And so it's increasing from 0, so from here all the way to infinity. And then it's decreasing from negative infinity, wherever that's going to end, which is nowhere, to 0, because then of course at 0 it's an asymptote. Then we have asymptotes and end behavior. So asymptote is a vertical, and so vertical lines are x equals 0. And then your end behavior just wants to know what's happening as it approaches certain ideas. And so the limit as x goes to negative infinity of the function, so as it goes this way, is going to be positive infinity. And then the limit as x goes to positive infinity is also positive infinity. So basically up at both of the ends. Alright, and then our last piece here, same idea. We're going to do our domain and range. And the function itself, oops. Well, that was not a straight line. Has an asymptote here at x equals 0, and then it goes through at 1 and kind of tapers off, but again it's an asymptote at x equals 0. So on that note, our domain stops at 0 and goes to infinity. Our range, however, goes all the way down and all the way up, so our range is going to be negative infinity to infinity, or all real numbers. Its continuity is continuous on its domain. We don't want to say continuous forever, because then if they pick any point, they might pick a negative number, which of course wouldn't exist, and so that would confuse people and think that there's maybe an asymptote or whatever, so you just say on the domain versus just continuous. And then we have our increasing and decreasing, and it turns out it's increasing always. Well, we'll just say on domain. And so we could technically write the domain, which is 0 to x to infinity. And then it's not decreasing at all, so we can say that that's not applicable or something. Right. Speaking of NA, I feel like people put that but don't know that it's not applicable. Last night we were watching something about the Titanic, and I said that SOS was save our ship, but apparently it's save our souls. Didn't even know that. Learn something new every day. I really thought my husband was wrong, but apparently he wasn't. Okay, moving on. Then the next one, decreasing, is asymptotes. So we mentioned it when we were graphing, but your asymptote is x equals 0 at a vertical asymptote. And then the end behavior is the limit as x goes to 0, because it's not going to infinity, is negative infinity. And then the limit as x goes to infinity is all the way up at positive infinity. So again, fancy way of saying it ends up and, down and up. Alright, there we are. So that was the 4-5 assignment, and hopefully, or 3-4 assignment, and hopefully that kind of felt like some algebra.